Why is that when you add two numbers, Python just knows what to do? Or when you use the len function on a list, it just works. But the second you create your own class, it all breaks. You get type errors, weird printouts, and your class feels dumb. What if I told you there's a secret set of methods that let you hook into Python's core behavior? You can teach your objects how to be added, sorted, printed, and even behave like list. This isn't just a trick, it's the key to writing truly good, professional, and easy to use Python code. Welcome back to day 6 of our Python object-oriented programming series. And in this episode, we are diving into one of my all-time favorite topics, magic methods, also known as Dunder methods. Dunder just means double underscore because they all start and end with two underscores like double underscore init double underscore. You have already been using one double underscore init double underscore the constructor, but there are dozens more, and they are Python's way of letting you define the magic behind your objects. This is the core of what we call operator overloading, making operators like plus, equal to, and multiplication work like our object. Magic methods are hooks. They are special methods that you don't call directly. Instead, Python calls them for you when you use certain syntax. So when you write len bracket mylist, Python actually translates that behind the scenes into mylist dot double underscore len double underscore method. Similarly, when you write a plus b, Python actually translates that into a dot double underscore add double underscore b. And when you write a equal to b, Python translates that into a dot dunder eq dunder b. The magic is that we can define these methods on our own classes to hook into those same rules. Let's build a simple 2D vector class. A vector is just a direction and power, usually shown with bracket xy bracket close numbers. Okay, I'm defining our vector class vector. We'll use our first magic method, which is a constructor. I'll pass x and y as an argument to the constructor, and inside the constructor, I'll just set self.x to x and self.y to y. Simple. Now let's switch to main.py file and let's try to use this class. We first import our vector class, then we create two of them. V1 will be vector with parameter x is equal to 2 and y is equal to 3, and V2 will be vector with x is equal to 5, y is equal to 7. Simple enough. We can create vectors. But now let's see what happens when we try to use them like we would use numbers or list. What happens when I print V1? I'll just run it. Output shows vector object at some location ending with 90. That's not helpful. It's just telling us where the object lives in the computer's memory. I want to see vector 2, 3. What happens if I try to add V1 and V2? Vector addition should just be adding the parts, right? Let's try V3 is equal to V1 plus V2. This should work, right? Let's run it and type error. Python has no idea how to add vector objects. We never told it. Now let's make another vector exactly like V1. So V1 copy is exactly like V1 with same data 2 and 3. So print V1 is equal to V1 underscore copy must be true, and the output shows false, but they are identical. This is because by default, Python's equal to operator doesn't check if the values inside are the same. It checks if V1 and V1 underscore copy are the exact same object in memory. They are not. They are two different boxes, even if they hold the same stuff. Our class is broken. Let's fix it, one magic method at a time. First, let's fix that printing issue. We have two magic methods for this, and it's very important to know the difference. Dunder str dunder for string. This is meant to be the pretty display for the end user. Print and str function will use this method. Dunder wrapper dunder for representation. This is meant to be the official, clear, and complete representation for the developer. It's what the console, log files, and debuggers use. A great wrapper should, if possible, be code that can recreate the object. Golden rule: you should always implement Dunder wrapper if Dunder str is missing. Python will fall back and use Dunder wrapper instead. So let's start there. We'll define wrapper method in the vector class or vector.py file. It is just taking self as an argument and returning a string. We'll return f string vector bracket x equal to parameterized on self.x, comma, y equal to parameterized on self.y, bracket close. See, that string looks just like the code we have typed to make it. I'm just going to type v1 into my console. Okay, let's just try this in Python console. I'll first import vector. I'll make a vector v1 is equal to vector with x and y value 2 and 3. Now I'll just type v1 and press enter. The output shows vector x is equal to 2, y equal to 3. So much better. And because we don't have a underscore str yet, print v1 will also use this Dunder wrapper method and print on the output vector x is equal to 2 and y is equal to 3. But what if we want print to be simpler? Maybe just in brackets 2, 3. So we can add Dunder str for that. So right below Dunder wrapper, let's add def Dunder str Dunder. This will also be returning a string, but a simpler one. So this f string will be just like a coordinate. Now watch. This is the key difference. Now, if I'll call print v1, it will show us 2 and 3. But console uses wrapper method. So if I'll again do v1, we'll get vector x is equal to 2, comma y is equal to 3. How cool is that? So now we have total control over how our object is displayed. The wrapper for the developer and str for the user. One problem down. Next, let's fix that type error and teach our vectors how to add. We want v1 plus v2 to work. As we learn, this will call v1.dunderAdd method with parameter v2. So let's define double underscore add double underscore. Let's decrease the size. Okay, let's define the dunderAdd method. Self is a vector on the left of the plus and the other is the vector on the right. Inside, we calculate new x equal to self.x plus other.x and new underscore y is self.y plus other.y. And this is super important. We return a brand new vector object with these new value, new underscore x and new underscore y. So I'm again breaking it down. We define dunderAdd which takes self and other. We calculated the new x and y coordinates and we return a brand new vector object with the result. Now back in main.py, we have v1 and v2 vectors and now let's try that failing line v3 assign v1 plus v2 and after that we'll print v3. Now I'm running it and yeah, it works. And print v3 is beautiful because of our Dunder str method is already doing its job. So our methods are working together. So how easy is subtraction now? It's the exact same pattern. Let's just quickly define Dunder sub method is just returning the subtraction of self minus other vector and it's done. Now we test it by calling v2 minus v1 and assigning the result to v2 which will call the Dunder sub method and we'll see what is being printed in v4. It shows 3 and 4. This is so powerful. We are making our class behave just like a built-in number. There are many more for these. Dunder mul for multiplication, Dunder true div for division. You can look them all up in the Python docs. Alright, let's fix problem 3, comparison. Remember v1 equal to v1 underscore copy gave us false. That's because it was checking if they were the same object, not if their values were equal. We can fix this by implementing Dunder EQ, where EQ stands for equals method. We define double underscore EQ double underscore method. The self is on the left of the equal to and other is on right side of the equality. We'll tell two vectors are equal if self.x is equal to other.x and self.y is equal to other.y. So they are only equal if both x and y are equal. Let's test it. So we have a vector v1 and v2. We will create v1 copy which is initialized with the same value 2 and 3 for x and y. Now we print v1 is equal to v1 underscore copy. This will call v1 dot dunder eq with parameter v1 underscore copy, and we'll also test whether v1 is equal to v2, which will call v1 dot dunder eq with parameter v2. Let's just run it and perfect. Now v1 is equal to v1 copy and v1 is equal to v2 is false. First one is true, which is both the vector have same value, and the second one is false. Perfect. Our class now understand what it means to have the same value. But what about other comparisons like less than or greater than or equal? This is where it gets really cool. These are called rich comparison. You have dunder LT for less than, dunder LE for less than or equal. We have dunder GT for greater than and dunder GE for greater than or equal. Do we have to implement all four? No. There's a magical helper in the func tool module called total ordering. If you import this and put @total ordering right above your class, you need to implement dunder EQ, which we did, and one of the other like dunder less than. Python will figure out all the rest for you. Let's do it. First, how we define less than for a vector. A common way is to compare their length, their magnitude or distance from the center. The length squared is x into x plus y into y. We can just compare those. Alright, at the top of the file vector.py, we'll write from func tool import total ordering. Then right above class vector, we add the decorator @total ordering. So over here are all our previous dunder method defined. Now we just need to add def underscore less than double underscore self comma other for less than. We calculate the length squared for self and assign it to magnitude underscore self. We do the same for other. Magnitude underscore other is square of x and y of other, and then we just return the boolean value whether max self is less than mag other. Now because we added total ordering and defined dunder EQ and dunder less than, we get greater than and less than equal to, greater than equal to for free. Let's check this by creating two vector v underscore small vector 1 1 and v underscore large vector 5 5. Now we can print v underscore small is less than v underscore large. This uses less than dunder method, but now we can also figure out whether v small is greater than v large. Python figured this out for us. Same for v underscore small is less than or equal to v underscore large, and v underscore small is greater than or equal to v underscore large. Let's run it and we can see all the methods are working perfectly fine and giving us true, false, true and false. It just works. This is how you write insanely clean, reusable and powerful classes. Okay, our vector class is good, but it's not great. What's its biggest weakness? It only works for 2D vectors. What if I want a 3D vector or a 5D vector for a data science? I would have to rewrite the whole class. This is a perfect opportunity to improve our code and show how magic methods make it easier, not harder. Let's rewrite our vector class. This time, it will accept any number of components. We are going to change gender in it. Instead of self xy, we'll write self comma star components. The star is a special Python trick. It scoops up all the argument a user passes in and puts them into a tuple called components. So vector 1 2 means components is a tuple with two values 1 and 2. Vector 1 2 3 4 means components is a tuple with four value 1 2 3 and 4. We'll add a check if not components, meaning they made an empty vector. We raise a value error where the text vector cannot be empty. Then we just save components into self.components attribute. But now all of our other magic methods are broken. They all assume self.x and self.y. Let's fix them. First, dunder wrapper and dunder str. For wrapper, we change it to return vector curly braces self.components. This will print vector bracket 1, 2, 3 bracket close. For dunder str, we return self.components. This will print bracket 1, 2, 3 or tuple components. Pretty nice and clean. Next, dunder add and dunder sub. This is the tricky one. We need to add component by component. The zip function is perfect for this. It pairs up elements from two lists. We can use a list comprehension to do the math and create a new list of components. But first, we must check that the vectors are the same length. You can't add a 2D vector to a 3D vector. Okay, so here is our modified dunder add and dunder sub method. Inside dunder add, we first check that if the length of self.component is not equal to length of other components, means if they are different, then we'll raise a value error with a string vector must be same dimension to add. If they are the same, then we'll use a list comprehension, new component assign list comprehension a plus b for a and b in zip self.component and other.component. So zip method pair them up, self first one and others first one, self second one, others second one. The list components add each pair. Finally, we return a new vector using star again to unlock our new list. And we do exactly the same thing for dunder sub method, just with minus sign. So the only change in add and subtract method is change of the minus sign. This is so much powerful that one add method now works for 2D, 3D, 4D, 100D, any n-dimensional vector. And finally, dunder eq and dunder less than is now super easy. Tuples already know how to compare themselves. So for dunder equal or dunder eq, this gets easier. We just return self.components is equal to other.components, and Python already knows how to check if two tuples are equal. What about less than or dunder lt method? We just need to sum the squares of all the components. So here for dunder lt, we add our length check first. Then for magnitude of self, we use sum with generator expression c to the power 2 for c in self.components. This squares every components and add them all up. We do the same for the magnitude of other and return the boolean value of whether mag self is less than mag other, just like before. But now it works for any size. And we are done. We have improved our class. It's now so much more powerful and our magic methods are cleaner than before. But wait, our new design unlocked a few more magic methods we couldn't use before. Our vector is now basically a collection of components. Doesn't that mean it's kind of like a list or a tuple? Shouldn't we be able to ask for its length using len function? Shouldn't we be able to get the first component with subscript v0? Yes, and there are magic methods for that. First, dunder len. This is what len calls. For us, it's just a number of components. This is the easiest one. Def dunder len dunder self, it's just return length of self.components. That's it. Now, length of my vector function or method will work. Second is getitem. This is what square bracket or subscript call. This is the big one. We define double underscore getitem double underscore self and with parameter index. Python will give us the index. The user put in the bracket. We just return the item from our own tuple. Return self.component index. This even gives us a slicing like v1 3 for free. There's also Dunder getitem, which lets you set a value with v0 to 10, but that makes our vector changeable, which is a whole other discussion. For today, we'll make it read-only, like a tuple. Now, for the final payoff, let's see a fully magic class in action. Okay, we'll create two vectors. One is a three-dimensional vector with value 1, 2, and 3, and another vector with value 4, 5, 6. Okay, and print f vector v3d that will use Dunder str, print len parameter v underscore 3d that will use Dunder len or Dunder len, print v3d subscript 1 that will use Dunder getitem and should give us 2. vsum is equal to v3d plus v other, that's Dunder add. Then we'll print vsum's value. And finally, v3d is less than v other, that's Dunder less than. Let's run it. That is a beautiful class. It's clean. It feels like real Python. It behaves like any built-in type, and anyone who uses it will know exactly what to do with it. This is the power of magic methods. Alright, that was a deep dive, but you have made it. Let's recap the core ideas. Magic methods are hooks. They are Dunder or double underscore methods that Python calls for you, not you directly. They let you hook into built-in syntax. Dunder str versus Dunder wrapper. Dunder wrapper is for developers. Clear, complete. Dunder str is for users. Pretty printing. Always make wrapper first. Arithmetic. You can always make operator like plus and work by defining Dunder add and Dunder sub. Always return a new object. Comparison. You can define how equal to work with Dunder eq, and by adding Dunder eq and Dunder less than or Dunder lt plus the total ordering helper, you'll get a rich comparison for free. Container behavior. With Dunder len and Dunder getitem, you can make your object behave like a list, allowing len function and indexing function. We took a dumb class that gave type errors and weird printouts, and we transformed it into a powerful, easy to use and Pythonic piece of code. This is what separates a beginner from a pro. Thanks so much for watching. I'm Sumantra and this is Sumantra Codes, and I'll see you in the next one.